chapter Dual Nature of Radiation and Matter. Today in the second lecture we are going to discuss the topics Hertz observations, Lennard's and Hallwachs experimental observations, and experimental study of photoelectric effect with different parameters. Those are photoelectric effect by varying the intensity of incident radiation, and the photoelectric effect due to the potential difference between the plates anode and cathode, photoelectric effect due to the frequency of incident radiation, and last one, the photoelectric effect by the nature of material of cathode. So we will go one by one. First we will go with the Hertz observation. In the Hertz observation, first we will study the setup. Hertz took two metal plates and between them he made an arrangement of metals in such a way that between them he kept two loops, and between those two loops he left a little bit gap. Then he wanted to study if ultraviolet rays fall on metal, then what may happen. Then he just made to fall the light on metal and immediately he observed a spark. Now he wanted to confirm whether the spark is due to light itself or not. Therefore he just blocked the UV light. Then immediately he observed there was no spark. So we can say he observed that high voltage spark across detector loop were enhanced when emitter plate was illuminated by UV light. Next we will go with the Lennard's and Hallwachs experimental observations. Philip Lennard and William Hallwachs conducted a detailed study of the phenomenon of photoelectric emission. When ultraviolet radiation fall on metal surface, immediately electrons are emitting. Observations indicate that when ultraviolet radiations fall on the emitter plate C, electrons are ejected from it, which are attracted towards the positive collector plate A. Therefore, there will be a current flow. Suppose if you block this one, that means no emission of electrons. Even no deflection in the emitter. Thus, light falling on the surface of emitter causes current in the external circuit. Let us go to the another scientist observation. William Hallwachs also took the study in further. He connected a negatively charged zinc plate to an electroscope. Hallwachs observed that the zinc plate lost its charge when it was illuminated by a UV light, and further he observed that uncharged zinc plate lost its charges and becomes positively charged when it was illuminated by UV light. And he concluded that negatively charged particles were emitted from the zinc plate under the action of UV light. The Lennard and Hallwachs, both they have observed a threshold frequency. We already know threshold frequency definition. Now we will go to the experimental study of photoelectric effect. Before that, we will understand the arrangement of the experiment setup. This is evacuated glass tube with a quartz window, sometimes that represents with a W, and C represents the cathode. We can say this as a photosensitive plate. A represents the anode. We can call this as anode, or we can say collector plate also. S represents the source of light, and the setup continues, and we are using a commutator to alter the direction of current. Sometimes we can give cathode to the positive direction, and even we can reverse also. Voltmeter helps to measure the voltage, and microammeter, which is connected in series at the external circuit, helps to measure the current. Rheostat helps to vary the potential difference. So here note these all points. We will study about this in further. When light of suitable frequency falls on the metallic cathode, photoelectrons are emitted. Let us check. So here when a source of light falls on cathode, immediately electrons are emitting towards the anode. So these photoelectrons are attracted towards the positive anode, and hence photoelectric current is constituted. That means current has been generated. Now as I told, if I change the intensity of this light source, and if I change the potential difference between the cathode and anode, and even we can replace the polarity also. So, in all these cases, maybe even we can change the plate, that is cathode, which we are having. If we make it with the different metals, then how the number of photoelectrons will emit, how the current varies, all these things we are going to study. Now, let us check one by one. So, graphically we are going to study here. First point, we will go with the effect of intensity on photocurrent. The number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation. So, here we will get the graph like this. Photocurrent is in the y-axis, intensity of light is in x-axis. And second point is effect of potential on photocurrent. We know the collector potential is meant for collecting emitted electrons. Initially, the current increases with increase in collector potential, after which it becomes some constant, or we can say saturates. When emitted electrons are equal to the collected electrons, that means it has reached a maximum current. So, that we call as saturated current. We can see in the graph, you can see here a graph which comes almost parallel to the x-axis. So, we can say current is saturated, or we can say that is saturation current. When the potential is decreased, the current decreases but does not become zero at zero potential. Now, we will observe in the graph. As the graph, we are taking the reverse order. Now, the question is, if we have to achieve the microampere, that should be 0, or we can say photocurrent should be completely 0. Then, as we already have taken in the previous picture, I told you by the help of this commutator, we can alter the direction. So, we call that as retarding potential. Now, we call that as negative potential, or we can say retarding potential. So, in this case what happened, even by increasing the potential difference in negative order, we will get photocurrent 0, but the point where it reaches 0, that will be in negative. So, that we call as a stopping potential, and we can say that minus P naught is the stopping potential. So, here what happens, the maximum kinetic energy, that means all the electrons will repel out. Now, we will go with another intensity. Suppose if I increase the intensity from I1 to I2, then how the graph will be? Even after the repeating the experiment, we are getting the graph like this. So, here again the stopping potential will be same for I2. Even if I increase the intensity for I3, in that case also the stopping potential will be same. Therefore, we can conclude as the intensity of incident light does not affect the stopping potential. Here I3 is greater than I2, which is greater than I1. And now we will come to the another topic, effect of frequency on photocurrent. For a fixed intensity of incident light, the photoelectric current does not depend on the frequency of incident light. Let us see by the help of graph. Here in the graph, we can say in y-axis photoelectric current, x-axis represents collector plate potential. In the right side we have positive, in the left side we are having retarding potential. Here this is a saturation current, which I am representing with the color pink. So, saturation current is here, and this is constant, but in the left side of the graph there are nu1, nu2, nu3, which represents the frequency in increasing order. So, as the frequency increases, the stopping potential also increases. You can say for frequency 1, stopping potential is minus V01. For frequency 2, which is more, that we can say higher frequency than first one, that is minus V02. So, similarly, if we increase the frequency, that is for nu3, the stopping potential is V03. So, we can say the stopping potential is more negative for higher frequencies of incident radiation. And last point is effect of photocurrent due to nature of material. Even for different metals, when we study, we can say the graph between frequency and stopping potential is always straight line and implies that there is always a minimum frequency below which there is no photocurrent. So in the x-axis we are having frequency of incident radiation. In the y-axis we have stopping potential. For two different metals, metal A and metal B, we have with different frequencies. So you can see in the graph, this represents a straight line. Similarly, for second also, this represents graph. Therefore, we can say it is reaching to the stopping potential 0, but frequency did not reach to 0. So we can say it has a little bit minimum frequency below which there is no photocurrent. Thank you, students. We will study some more points in the next classes. Thank you.